Hi, everyone. I'm Nick. I'm a postdoc in EASY, and I'm here today to introduce our speaker, our colleague, Dr. Maureen Feineman. Maureen is a hard rock petrologist and high temperature geochemist who specializes in fluid transfer in subduction zones. She has a PhD from UC Berkeley and was a grad research fellow at the Lawrence Livermore National Laboratory. After that, she did a postdoc at the Institute for Study of the Earth's Interior in Misasa, Japan. And she's currently at Penn State, the director of the Geoscience program in Energy and Environmental Resource Sustainability, aka the GeoPeers REU. She divides her time between the Department of Geosciences and the Minerals Characterization Lab. And she's going to talk to us today about rare earth elements in waste products from mining and smelting in Pennsylvania. So give it up for Maureen Feineman.
Thank you, everybody, for joining me here today. I'm going to be talking about work that I've been doing more or less since the pandemic. I think a lot of us kind of slowed down during that time period and started looking around us more instead of thinking about what's the farthest place I can possibly go from here to study geology, and started looking to Pennsylvania. And one of the more interesting things that I found here was looking at some of the history of mining and of mineral processing and smelting in the iron furnaces across the state. So today I'm going to be talking about a critical legacy, rare earth elements in waste products from historical mining and smelting in Pennsylvania. This is work that I have been doing with colleagues Barb Arnold in energy and mining engineering and Joshua Garber in geosciences, formerly here in geosciences, now at the University of St. Andrews in Scotland, where there is more smelting and more mining to be studied. And also want to acknowledge some undergraduates who were really critical in doing a lot of the work on this project. Noah Sheldon, Sarah Ambrazak, and Aaron Scheckler, the first two being geosciences senior thesis students, and the third being an REU who worked very hard on this project over the summer. All right, so in the 18th and 19th centuries, Pennsylvania was an industrial workhorse. Energy production during this time was transitioning from charcoal to coal and oil. There was a strong demand for iron that was fueled by the Revolutionary and Civil War, and then coming into the beginning of the Industrial Revolution. Pennsylvania had all the raw materials for iron production. We had iron ore, we had limestone, and we had charcoal, and then later coal as we transitioned from charcoal burning furnaces to coal burning furnaces. And iron was produced on iron plantations across the state, and that includes the center furnace right here practically on campus. And really the reason why Penn State is located, University Park is located specifically where it is because land was donated from the center furnace to the university to start the Farmers High School. Fast forward to the 21st century, Pennsylvania, we have an increasing share of our energy that's coming from renewables. We're using wind power in particular. If you drive down 99, you'll see all the wind turbines off the Allegheny front. The demand for critical minerals nationwide is being fueled by the tech industry and the green energy revolution. There are actually rare earth elements are needed to make the magnets that convert the wind energy, the kinetic energy of the wind rotors into electricity. So that power source cannot happen without the production, mining, processing of rare earth elements as part of the larger critical mineral portfolio. And so the question I guess we started out looking at was, can the waste products of 18th century industry guide the way to meeting today's tech and energy needs by helping us to understand a bit more about the geology of the resources that were not yet on the radar at the time that this grand era of iron production was happening in Pennsylvania. So just an overview of where I'm going, talk a little bit about rare earth elements, go into the history of iron production in Pennsylvania and a little bit about the geology of Pennsylvania iron deposits. Mostly going to talk about chemical characterization of historic iron slag and mine tailings in the state. And then going to take a little time at the end to talk about something called the honorable harvest and thinking about a mindful approach to extractive geology at this crossroads where we have a moment to look back on the past as well as forward to future needs. So critical minerals are defined by the U.S. Energy Act of 2020 as any non-fuel mineral, element, substance, or material that the Secretary of Energy determines has a high risk of supply chain disruption, serves an essential function in one or more energy technologies, and that includes the technologies that produce, transmit, store, and conserve energy, but not the generation of the energy, or the, not non-fuel minerals. And they can also be defined by the Secretary of the Interior. There is a USGS list that gets updated every year. I think I just saw rhenium was the most recent material to be added to the list of critical minerals. There are about 50, I think it's gone up a little bit since I first made this slide, but about 50 elements on the periodic table that are currently designated as critical. And the graph here, it shows one way of assessing critical minerals by plotting the supply risk from low to high on the x-axis and the importance for energy technology development from low to high on the y-axis. So that upper right corner is going to give you the most critical of critical minerals, the materials that we need the most for energy and also import the most of or are most reliant on imports of. And you'll notice that many of the rare earth elements show up in that red box area up there. So rare earth elements, these are the lanthanides. They're that bottom, well, the top of the bottom two rows of the periodic table. In terms of overall rarity, so this figure here plots kind of how from lightest to heaviest elements on the periodic table and then their abundance in the crust relative to silica. So it's per 1 million atoms of silicon. So the silicon plots right at 10 to the 6 per 10 to the 6. The rare earth elements are shown in light blue. And you'll notice, I guess one thing that really struck me when I looked at this is rare earth elements are about as rare as tin. And we don't typically think of tin as being a high value critical element. So they're really in kind of the mid range. They're not in that kind of handful of the very most common rock forming minerals, but they're also not in the rarest of rare metals. And another thing to mention just about what we mean when we say rare earth elements are everywhere. Every time you step outside and you're walking on dirt, on soil, on bedrock, there are rare earth elements under your feet. There's just a very, very small amount of rare earth elements under your feet. So rare doesn't mean they're not there or they're hidden away somewhere. It just means that for the most part, they are distributed widely, which makes them very difficult to condense and make into a useful form. And then on the right is all the uses of rare earth elements. And again, one of the more important of these is energy technologies, fuel cells, energy storage, also computer drives, many, many applications that are using rare earth elements. So I'm going to wind back now to early 18th century, mid 18th century. Iron production is taking off, starts in the southeastern part of the state in these what's called a cold blast furnace. These furnaces were fired by charcoal. They had a air bellows that was powered by water, by a water wheel. And the basic chemistry for what's happening here is that the oxygen in the air that is being pumped through with these bellows reacts with a carbon-based fuel source. Again, in the early days up until about 1880s, they were using charcoal, and then around that time they started transitioning to coal, which in burning in combination produce carbon monoxide. That carbon monoxide then reduces the iron oxide in the ore, the product of which is metallic iron and carbon dioxide. There's also a limestone flux that is used to help with the melting and purification. And it's the non-iron minerals in the ore together with that limestone, the calcium coming from the limestone, that are producing the slaggy waste product. The useful product at the time was pig iron. So the bottom of the furnace was tapped and the iron was allowed to run out into troughs in the sandy floor of the furnace that generates these iron pigs. That was the raw commodity, and then they could be shipped and further processed. The molten slag is less dense than the iron. It floated up to the top and could be tapped off from a separate hole, and then either poured out onto the floor right there for the smaller, earlier cold blast furnaces. Later, when we got into massive production from hot blast furnaces, the slag was carried off on big cauldrons on little trains and dumped usually over a hillside. If you're looking for slag at what you know to have once been a furnace site, the thing I usually do, either look for a hill, because the hill is often a slag mound, or look for the nearest steep slope, because they probably were dumping it over the steep slope, and so you'll often find it along stream banks. This is a map that was made by senior thesis student Sarah Ambrazak that plots the location of furnaces in Pennsylvania as a function of their age, with red being the earliest furnaces starting in 1737, and then going through orange, yellow, green, blue being the youngest of the cold blast furnaces. Those actually, these aren't all cold blasts. I'll talk about that as well. Up through 1884. The cold blast furnaces are shown with a little snowflake. The hot blast has a furnace droplet there. And some furnaces were converted from cold blast to hot blast. Also shown are coal fields in gray, and the iron ore are the dark gray lines, and streams. And again, the furnaces are always co-located. They're going to be close to the ore source, and they're going to be located on a stream, because that's how they were powered, how the bellows were powered. A lot of really interesting information that comes out of this map, actually, but one of the things that we didn't really notice until looking at it this way is that the earliest furnaces are all down in the southeast corner of the state, Chester County, down around Philadelphia, moving out towards Cornwall. And then Over time, they spread to central Pennsylvania around here. We were kind of like the great middle age of the iron furnaces, and then only later do they really get up into the northwest corner. Mostly that's happening as bituminous coal is really getting going, and that was used as a fuel source to power those furnaces up in there. So just power of geodata in action. This is just looking at a geologic map of the state of Pennsylvania to point out that there are really two main categories of very different types of iron deposits in Pennsylvania. Down in the southeast corner where the early iron mining and smelting was done, those are skarn deposits that are associated with Jurassic-Triassic intrusion of diabases into the Rift Valley there, as we have the early opening of what is going to be the Mid-Atlantic Ridge. This is like part of the Camp province of flood basalts, and these run right across the southeast corner of the state. And then the rest of central and western Pennsylvania, those are sedimentary deposits. There are two different ages of sedimentary deposits, but nonetheless, they're sedimentary dissolution precipitation source. So I'm going to start quickly. I'm going to go through this part a little bit quickly so we can get to the chemical data. But we start with the Cornwall type skarn deposits down in the southeast part of the state. These were precipitated from magmatic fluids that were again created during those Triassic diabase intrusions as they reacted with Precambrian and Cambrian carbonates. Those were both metamorphic and sedimentary rocks forming those skarns. They're magnetite skarns with secondary pyrite and chalcopyrite. And then they often are accompanied by garnet, diopside, epidote, allanite, which I bolded because we're going to come back to that one later, actinolite chlorite, recrystallized calcite, copper, cobalt, and minor gold and silver were also present in the sulfides, and in some cases in quantities enough to be mined. So Cornwall furnace itself, for which the Cornwall type deposit is named, that was a cold blast furnace up until 1883, processed the local ore, also refined copper from chalcopyrite. Cornwall is also known for being a cobalt-bearing ore, and that cobalt was not processed on site at the furnace, but was sent away to be processed, I believe somewhere in the northeastern part of the state. That furnace was ultimately shut down and a new hot blast furnace opened on the same property. That's the Bird Coleman hot blast furnace. That was in operation from 1872 until early 20th century. Lots and lots and lots of iron were produced at the Bird Coleman hot blast furnace. And as a result, lots and lots of slag. There are whole stratigraphic sequences of slag piles that were dumped on site there. Also nearby is the French Creek mining area. This is a little bit unique in that the diabase intruded into Precambrian graphitic gneisses, and we see that actually does end up having a bit of an influence on the composition of the ore and of the slag, which kind of leads us back to looking at the ore again. The ore from French Creek mining area, which was several mines, was processed at the Hopewell furnace from 1771 to 1883. This is now a National Historic Site. You can go and visit, but you can't take anything. We have a couple of samples that were given to us by the curator there. And then the Joanna furnace nearby, which is maintained by a local historic organization, volunteer organization. And that was there from 1792 to 1901. Slag pile is still on site there, and you can pick through, again, look for the hill and then go dig through the dirt, and you'll find the slag there. In central Pennsylvania, we have limonite ores. These are widespread iron disseminated in sedimentary carbonates, siderite in carbonates, uplift, erosion, and karst weathering brought that iron into solution. It was dissolved in reduced water near the surface, we think, in shallow ponds and sinkholes, and then reprecipitated as limonite, mostly as goethite, deeper when it was oxidized in contact with the water table. I credit this to Rudy Slingerland. I don't know if you drew this yourself or, okay. Okay. So this is a recreation of art's art. Just an idea of the iron precipitation, often in these kind of almost stalactite-like dripstones and pipe ores, as well as in lumps and disseminated throughout the clay and sand. Closest into here was the Scotia mines, which is part of the larger Pennington Bank. These were mined from the 1700s to the very early 1900s. Again, mostly goethite ore. You can see some cross sections. We cut through a few of the pieces we found there where you can see these sort of in the upper right corner, that's like a slice through a stalactite kind of dripstone. And below it on the right is rotated, but that's also an iron dripstone. Lower left is pipe ore. So that's precipitated on the walls of kind of a cavernous opening. Not a whole lot to find. In fact, I would say the best thing you're most likely to find at Scotia these days is probably ticks. It's very grassy and swampy, and you can find a couple of pieces there, but it's a lot of work for a little bit of payoff to find anything there anymore. But that is our local iron source. Center Furnace, as I mentioned, and as you have certainly driven by, perhaps you have visited, was 200 acres that was used to house iron workers and to run the furnace there. They processed ore from Scotia and other local sources. And this is how this whole project got started, is by looking at slag from the center furnace. One of the historians there asked us if we could figure out why it's green. We took a look at it, and then from there, thought, well, what else might be in this slag and what can we learn from there? So that was what started kind of the whole adventure. We also have Greenwood Furnace nearby, local iron sources within 3 miles, some of which are still accessible by hiking. There is a big overgrown slag pile still on site there along the banks of the creek. And then Curtin Village and Eagle Iron Works, also you can go and visit. They have a very nice self-guided tour. You can arrange to have someone meet you there. There's less slag, but there is still some slag still on site there. So what is slag? As I mentioned, this is the waste product of the iron refining. This is all the stuff that's not the iron that floats up to the top. It's mostly silicon, aluminum, calcium, magnesium. It has all the trace impurities that are separated, which makes it actually a really good way of understanding what was co-forming with the iron ore. Sometimes it contains chunks of unprocessed ore, of limestone, charcoal, sand sometimes. And we also find dendritic crystals that are growing within it. It's essentially calcium, magnesium, aluminum, silicon system, and we get all the minerals you might expect to grow in a calcium, magnesium, aluminum, silicon system. just a wee bit of iron. This is looking at the major element compositions of slags from all of those furnaces I just showed you. And again, the major component is silicon, calcium, and aluminum, then being the next most important. Those igneous skarn formations down in the southeast corner produced magnesium-rich slags. Whereas the western, oh, this only has the central ones. As we come up into the center and then into western Pennsylvania, we get a little bit more potassium from clay inclusion in the slags. Next, we looked at rare earth element abundances in slag. So these are the original sample set we had from center furnace. We found that the rare earth elements are generally in about 600 to 800 parts per million in the slag. And as a point of reference, broadly speaking, once it gets up over 300 to 500 parts per million is when people start to look kind of seriously at something to see, does this have potential as a rare earth element source. Some of the samples had upwards of 1,000 parts per million of rare earth elements going to Greenwood and Curtin. Similar story, 600 to 800 on average, in some cases up over 1,000 parts per million total rare earth elements. Joanna and Hopewell down in the southeast corner, highly variable, anywhere from just a couple hundred parts per million, again, up into excesses of 1,000 to 1,200 parts per million. Interesting to note, though, that regardless of the geology, regardless of the style of ore formation, we're getting high rare earth element abundances in slags kind of across the state. So this is now looking at the rare earth elements in slag samples versus average or normalized to average upper continental crust. So this is saying if I were to pick up a piece of slag, how much rare earth element does it have in it compared to any other rock that I might pick up if I walk outside on any given day. And in general, these slag samples are enriched by up to maybe a tiny bit in excess of 10 times what is typically found in your average upper continental crust. The enrichment is heterogeneous, so not every piece of slag is going to have high rare earth elements in it. And also the enrichment is broadly independent of the type of ore, of the geologic setting. We look in southeastern Pennsylvania, central Pennsylvania, western Pennsylvania, all in that kind of 1 to 10 times upper continental crust. And another interesting feature of these, the middle and heavy rare earth elements are much more valuable than the light rare earth elements. Light rare earth elements, back on that first, I don't think I pointed it out specifically, but on that plot of units of atomic number versus the abundance compared to silicon. The lanthanum, cerium, praseodymium are like half an order of magnitude higher than the middle and heavy rare earth elements there. So interested in particular to note that it is the middle to the heavy rare earth elements that are particularly enriched in these materials. Looking at principal component analysis of the slag samples, a few takeaways, none of which are surprising based on anything else I've just told you. The rare earth elements tend to cluster together. So if a rare earth element is high in a sample, all of the rare earth elements will generally be high in that sample. That's useful, and it's also true of yttrium as well. And that's useful because yttrium is easily detected with a handheld FTIR instrument. So that means it's pretty easy, now that we know this, to kind of go out and find rare earth enriched slag samples. Central Pennsylvania actually had the most, those are the blue dots on there, actually had the closest association with rare earth elements. Whereas the Cornwall type had a higher association with magnesium and copper compared to other samples. And the Appalachian Basin slags had a higher association with potassium, rubidium, and cesium, which is consistent with there being some clay associated with those sedimentary samples. And all of them show some stretching out towards the transition metals, which is basically a function of how efficiently the iron was removed from the slag and the slag samples. And this is just sort of an overall summary of what we know so far. So the red dots are southeastern Pennsylvania, green are central Pennsylvania, purple are northwestern Pennsylvania, and the dot size corresponds to the abundance of total rare earth elements. So again, we find high concentrations in excess of 1,000 parts per million everywhere across the state, and most commonly high in central Pennsylvania around us, most mixed, actually mostly lower in western Pennsylvania with just a few higher concentration ones, and then some medium high down in the southeastern part of the state. All right, so I'm going to move this. That's kind of overall slag, but what does that like? Are we really going to start remining slag, reprocessing slag? How do we get rare earth elements back out of these glasses? There are a lot of people who are, or some people who are working now on processes to reclaim rare earth elements from glassy, calcium-rich matrices. In addition to iron slags like this, also looking at reclaiming rare earth elements from fly ash, which is compositionally similar on hole. So there is some movement towards trying to break down and reclaim rare earth elements. But also, this is clearly like if we're looking at 19th and 18th century slags, this is a finite resource. There is only so much cold blast slag to be had. In addition, however, it leads us to think about what are the processes that are concentrating rare earth elements, where are they coming from, and can we find these in other materials from these sites? We got a hold of just a couple, actually, this is Barb Arnold, got a hold of a couple of old mine tailings from the French Creek mining area, and we had like 2 mez and then like 1 really like wildly over 2,500 parts per million total rare earth elements in one of the mine tailings from French Creek. So this brought up some new questions. What remains of these historic mine tailings? We're trying to track them down right now. We have a trip next week going out to a potential site of mine tailing storage. How are the rare earth elements hosted in the mine tailings? And is there a rare earth element bearing phase that we can separate and concentrate? So this took us to this summer working with REU student Erin Scheckler. And working with a brand new toy in the materials characterization lab. This is a automated mineralogy scanning electron microscope. This allows us to scan particulate samples and do particle counting and phase identification automatically. So this is a mount. What you're looking at, the colored slide, is an epoxy mount of the mine tailings, or of a size fraction, sieved size fraction of the mine tailings. Each color on there is a different mineral. The yellows are pyrite, the orange is chalcopyrite, and there's this kind of purpley pink color that is all of the allanite crystals in this sample. So allanite is a rare earth element bearing epidote group mineral. So then what we did from there in the lower right-hand image is an overlay of all of the rare earth element phases on top of a backscattered electron image. This allows us to go in and pick out individual crystals of interest to look at more closely, or particles to look at more closely by other methods. This took, months worth of work and did it in a day and a half. Really, really interesting and exciting new technology if you're working with particulate samples. So from there, we were able to pick, and there's the two yellow circles there are the two crystals that I'm going to show you in more detail. Overall, the sample had about 2% allanite in it, and then we were able to take it over to the electron microprobe and map the rare earth element concentrations in those individual grains. They are zoned, but high concentrations total in this particular grain of about 15 parts, or I'm sorry, about 15 weight percent total rare earth elements in the allanite grain. Allanite is also a weakly magnetic mineral, so in comparison to the highly magnetic magnetite and sulfides, can be separated magnetically in one pass, and then the silicate and carbonate minerals can be separated out in another pass. That should leave us with a strongly epidote enriched middle segment. So we do think there's potential for separating the rare earth element phase from these mine tailings. We also noticed that some of the crystals, like this was a whole fragment that was just one piece, and you can tell from the zoning that it's broken off from a still larger allanite crystal. We also found some cluster particles that were magnetite and allanite co-precipitated. And so this would suggest that at least some of this allanite was being mobilized together with the iron-bearing ore fluid and reprecipitated. And what we think is happening here, the Precambrian gneiss that the diabase is coming up through is an allanite-bearing graphitic gneiss. Some of what we're seeing in the mine tailings is probably just bits of that gneiss, whereas some of it is allanite that was dissolved and reprecipitated. Okay, so that's our story with the mine tailings, and I think this is probably the most promising thing we've seen so far in terms of taking like step by step. Seems to be some enrichment of rare earth elements in the iron slag. Can we go then to the source where it was mined from? What other waste products do we have there? Narrowing down to at least one place where we can see what the host of the rare earth elements are and how identify that as a separable phase that can be processed separately. I just wanted to take a minute to pause and talk about, I don't know if anybody here was here 2 years ago when we had Robin Wall-Kimmerer come to visit. This was a really exciting, she came, her MacArthur Prize was announced 2 days before she came here, so everything was fresh and exciting. We all read her book, and we talked when she was here about critical mineral mining and how we can take a more responsible, more conscious kind of taking a pause moment where we stop doing a whole lot of mining and then looking forward to, okay, let's start doing a lot of mining again. What are ways in which we can incorporate more responsible practices into our approach to mining? And this question was posed to her, and she said, well, I don't really know. It's a hard question, which we all know. This is a really hard question. We need critical elements. We need technology. None of us is ready to give up our phone or give up our electric car, our wind power, our iPad. But producing those materials domestically means there are going to be impacts. And she said, I don't really know what the answer to this is, but there is a way of approaching harvesting that could potentially be applied, at least some aspects of it perhaps could be applied to the way we approach mining. And these are just a couple that if you're interested, I strongly recommend reading chapter 17 of Braiding Sweetgrass, which is the chapter about the honorable harvest. There's a lot of really good information, good wisdom, some of which can be applied to what we are doing in there. And some of the ideas are things like ask permission before taking, listen to the answer, take only what you need. And I think this is one big area for us to define what is it that we need rather than just take everything we can find. How much of these things do we need? Leave some for others. And I think another way of thinking about that is leave some for the future. Harvest in a way that minimizes harm. Use what you take respectfully, do not waste. And this comes down to, I think, efficiency. It comes down to recycling of resources, to thinking about ways of using less, consuming less energy as a part of our total energy portfolio. Reciprocate, give back in return for what is taken, be grateful, and be accountable. And again, these weren't necessarily concepts that were built with mining in mind, but nonetheless, they are good guiding principles that we have the ability and the moment now to think about as we look forward to thinking about how we are going to continue in extractive industries, and not just continue, but really ramp up, because that seems to be where we are right now. So in summary, rare earth element concentrations are highly variable in slags and in mine tailings. The concentrations don't correspond clearly to a given geologic setting or ore type. They are enriched generally in, the slags are enriched by up to 10 times average upper continental crust, whereas the mine tailings contain separable phases such as allanite with up to 15 weight% of total rare earth elements. The lack of correlation with a geologic setting suggests that ore fluids may mobilize and reconcentrate the rare earth bearing minerals under conditions that are similar to those of iron mobilization and precipitation. We have a valuable lower impact source, perhaps, of some critical minerals in our mine tailings. And, we all know that extractive industries will always come at a cost. There will be impacts, but we do have the opportunity to think about the impacts that we are going to have, and to minimize those impacts to the best of our ability if we think about it, if we try, if we care. And that's it.
Thank you, Maureen.
Yeah.
All right, we can take questions, and we're going to use the catch box today. So, anybody have a question in the room?
Maureen, for the ores around here, what do you think the concentration is of these rare earth elements relative to just the residuum, say, in the Gatesburg? I mean, is there any hope that one would come back into the Gatesburg and run a full-scale mining operation that would be profitable, not only because of the iron ore, but because of the rare earths?
At this point, we don't have anything to point to suggest that is the case. So unlike the French Creek, where we can say there's the allanite, that is the phase that holds it. We can figure out how much allanite there is, how much mine tailings there are, and what is accessible there. We don't have that information for locally. I think that is a really interesting question and is actually one that I would like to look at in more detail, because it's clear from looking at the slag that our local iron ores here have at least as much rare earth elements in them as there are in those from southeastern Pennsylvania, if not more. So I think there's potential, but we don't know enough yet about how those rare earth elements are hosted in there to say if that's something worth going after.
I have the
Yeah.
box here, whatever. Thank you for this talk. I really thought it was fascinating, and I especially enjoyed the historical overview. If you're determined not to, destroy again the sites that were mined in the 17 and 1800s, you might think about modern iron making. And I was curious whether you have gotten any modern slags and analyzed those.
So far, here's what I can tell you about that, because it's taken a little. We did get some modern slags, and they were so completely different from the historical slags that at first I didn't even really know what to do with them. I think the reason for that is the processing. So the slag, what is being given to us as modern slag, is slag of steel production. That iron has already been purified once before it gets there. So I think we're just not getting, like, we did request modern slag samples, we did get modern slag samples, and they were these weird metal oxide things, not these waste products of the original smelting. So I think the question is, like, where is that iron slag? Because when you start asking for slag, the stuff that people start sending you is not that. So I think it's got to be somewhere, and I think there's a good chance, again, I think we're just one little state here. So I think there is a lot more looking to be done in other places. But we do also know that there are magnetite, apatite deposits around the world. I think it is reasonable to expect that most iron deposits are going to have rare earth elements in and with them. And the reason is because the conditions, the fluids, the dissolution and the precipitation conditions for iron are similar to the conditions that are going to dissolve and precipitate the rare earth elements.
All right, I do have one question on Zoom from Fandy.
Mhm.
Do you want to unmute yourself and ask your question?
Thanks, Maureen. Thanks, Everly. Maureen, thank you for the presentation. And I have a question. You touched here and there in bits and pieces around the separability of
Yeah.
the rare earth elements, and I think you've what's the word? You've continuously referred to this as sources, not resources, at this point. So
Yeah.
I'm just trying to get a sense of, in the characterization work that you have done, how far have you gone in terms of ascertaining that separability, and where can the metallurgist pick up from you in terms
Yeah.
of the data you have to actually then look at those aspects to do with processability, and just where you can also then come back in to now characterize the gang, because once it's processed, we need to know what didn't extract and why it didn't extract, and the same tools that you've used at play. So if you could just kind of like comment on that aspect around separability, what efforts and information you have towards that.
Absolutely. So there's two separate answers depending on if we're talking about the mine tailings or if we're talking about the slag. I'll start with the mine tailings because that one's easier to answer. So for the mine tailings, in particular these French Creek mine tailings, you can identify a separable phase, right? That is the allanite. We can account for all of the rare earth elements in the bulk assay by that 2% of allanite with 15 weight percent in it. So that can be concentrated. In terms of breaking down the allanite then, so that gets us to a 10 to 15 weight percent separate there, concentrate. I leave it to my mineral engineering friends to determine how to break down the allanite. We can get you that far. We can get you that far with it. The calcium, I am hoping to start working with colleagues at the National Energy Technology Laboratory. We have a couple of graduates of the PhD program here in geosciences at Penn State who are now working at the National Energy Technology Laboratory in Pittsburgh. And one of the things that they have been working on, reportedly with some success, is a method to break down calcium-rich matrices to extract rare earth elements and other refractory metals from them. So that's something I hope to be more involved with in the coming year. But there is no, because I get this question a lot. I think we've probably, Tandy, talked about this a little bit before. There is no high rare earth element phase within the slag that can be mechanically separated the way the allanite can be separated from the mine tailings. The slag is glassy. The glass is heterogeneous, but the rare earth element, the host of the rare earth element, is the glassy matrix. So when we're talking about potential for getting rare earth elements out of those slags, we're talking about breaking down the glassy matrix. And there are potentially, again, there are many people who are working on this and similar problems. There is the potential to create a bigger problem than we started with when we start taking these heavy metal bearing glasses. Right now, all the nasty stuff is very safely hidden, tucked away in these glasses, and they can sit out in soil and in water, and they leach very little, actually. So they're very nicely made inert by being stored in these glasses. It also makes them hard to get back out again without creating, we don't want to create some kind of toxic acid mine waste problem by breaking these down. I guess one other thing I'll mention about these furnaces that were so active in at the start of the Industrial Revolution is these were one of the major outchuggers of carbon dioxide. They were burning carbonate for the purpose of generating carbon monoxide and converting it to carbon dioxide. Another potential use of slags is for carbonation. So that's another process that chemical engineers are working on, is recarbonating, and potentially, I guess the dream would be to have a process that would simultaneously or in two steps remove the metals of interest and carbonate the residue to recapture some of the carbon that was released during the original processing of these. Recarbonate what was once carbonate rocks.
All right, thank you, Thandi. I do have one more question on Zoom from David Russ. He said, are there still economic deposits of magnetite at Cornwall? If so, might REE be co-produced?
Oh, so Cornwall does not have, based on everything we have measured so far, does not have rare earth elements. Cornwall, what is exciting or potentially of interest there is the cobalt and the copper. what remains at Cornwall, they stopped mining after Hurricane Agnes. So the mine was continuously active up until 1972. It flooded in Agnes, and that was when they stopped. So potentially yes, there is still ore at the bottom of the flooded pit there, that if anyone ever wanted, if there were enough interest and enough value in opening Cornwall up again. There almost certainly is. I will also say I was just out there over the summer. They are currently flattening the dump, the original mine dump there, to build housing on top of. We're any mineral collectors here, go out to Cornwall on a Sunday when they're not moving heavy machinery around there. It's crawling with rock hunters, pyrite, chalcopyrite, all kinds of cool, some malachite there, cool stuff.
Any more questions in the room?
Got one.
Have you published this material anywhere?
We have not published it. We are compiling the slag portion of it to publish as a survey of slag compositions in Pennsylvania. The mine tailings we are presenting at a couple of conferences this fall, but we're still not sure where the bulk of those mine tailings are. So we're keeping that one a little bit quiet until we figure out where the tailings are. We have a lead, and we're going out first week of October to try and see sample a tailings pile and see if it's the one we're looking for. But yeah, we were given a bag of tailings by a retired state geologist that turned out to be absolutely fascinating, but no one knows kind of where the mother lode of those tailings are. So that's what we're on the hunt for right now.
Why are the slags colored bluish green?
Oh, so iron. Iron is the very non-exciting answer to that question. And actually, it's actually, at first I thought it was uninteresting. Then I found out it's way more interesting than I realized. So there used to be like the furnace master would read the color of the slag to determine how the chemistry of that batch of iron was coming along. And if it was, green would be less efficient subtraction. Green or blue would be a less efficient subtraction of iron. They might need to add a little more limestone, add a little more charcoal. So they would look at the color of the slag, just tap a little bit, look at the color, and adjust the ingredients into the furnace on the basis of that. But it's just a tiny bit. There is one, we had read in a couple of places that the green color came from manganese, and we couldn't find anything to support that until we found at Cornwall this weird shade of green that was different from any other green we had collected. So we grabbed some of that one, and that did turn out to have manganese in it. So there is one shade of green, but it's not the common blue, turquoise blue green one that you are used to seeing that may have manganese. Most of it is just a little more iron. Maybe it's got 1% or 1.5% of iron still in it.
All right, it's 5 o'clock, so that's about all the time we have for Maureen. We can thank her again.
Thank you.
There is no seminar next week, but the week after that, we will start up again and basically have one for every Monday other than holiday breaks and stuff like that. So yeah, thanks guys.